This is SpaceTime, Series 20, Episode 27. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, SoundCloud, YouTube, Audio Boom, direct from spacetimewithstuartgary.com, or from your favourite podcast download provider. SpaceTime is also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world through TuneIn Radio, and as in-flight entertainment aboard Virgin Australia. Coming up on SpaceTime, how the Martian atmosphere was lost to space. Why isn't the rotation of the Earth slowing down as fast as it should be? And SpaceX launches into history with the second flight of its reusable rocket. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New results from NASA's MAVEN spacecraft have confirmed theories that the solar wind and radiation from the sun have been stripping the Martian atmosphere, transforming the red planet from a warm, wet world which could have supported life billions of years ago into the freeze-dried desert it is today. The findings, reported in the journal Science, are using measurements of today's atmosphere on the red planet to provide the first estimates of just how much gas has been removed from Mars over time. The study's lead author, MAVEN principal investigator Professor Bruce Jakosky from the University of Colorado in Boulder, says about 65% of all the argon that was in the Martian atmosphere has now been lost into space. Liquid water, essential for life as we know it, isn't stable on the Martian surface today because the atmosphere is too cold and too thin to support it. However, evidence of features resembling dry riverbeds and minerals that can only form in the presence of liquid water indicates that the Martian climate was warm enough in the past and the atmosphere thick enough for liquid water to have run across the surface for extended periods. There are many ways a planet can lose some or all of its atmosphere. For example, chemical reactions that lock gas away in surface rocks. Or an atmosphere can be eroded away by radiation and wind from the planet's star. The new MAVEN results reveal that solar wind and radiation from the sun were responsible for most of the atmospheric loss on Mars, and that depletion was enough to transform the Martian climate. The solar wind is a thin, continuous stream of electrically conducting gas constantly blowing from the sun. Young stars have far more intense ultraviolet radiation and solar winds. So atmospheric losses through these processes was likely far greater early in the red planet's history. And it's these processes which may have been the dominant ones controlling the planet's past climate and habitability. It's possible that microbial life could have existed on the red planet's surface early in Martian history. But as the planet cooled off and dried up, any life would have been driven underground or forced into occasional or rare surface oases. Jakosky and colleagues obtained their results by measuring the atmospheric abundance of two different isotopes of argon gas. Isotopes are atoms of the same element but with different masses. Because the lighter of the two isotopes escapes into space more readily, it leaves the gas remaining behind enriched in the heavier isotope. The team used this enrichment, together with how it varied at different altitudes through the atmosphere, to estimate the fraction of atmospheric gas that has been lost into space. As a noble gas, argon doesn't react chemically with anything else, therefore it wouldn't get sequestered into rocks. Therefore, the only process that can remove it would be a physical process known as sputtering caused by the solar wind, and that would have the effect of bouncing argon into space. In sputtering, ions picked up by the solar wind impact Mars at high speeds. They then physically knock atmospheric gases like argon into space. The team tracked argon because it can only be removed by sputtering. Once they determined the amount of argon lost by sputtering, they could use the efficiency of sputtering on Mars to determine the sputtering loss of other atoms and molecules, including carbon dioxide. Carbon dioxide is of interest because it's a major constituent of the Martian atmosphere, and because it's an efficient greenhouse gas that can retain heat and warm the planet. Jakosky says his team determined that the majority of the planet's CO2 was also lost into space as a result of sputtering. Now, it's worth pointing out there are other processes that can also remove carbon dioxide, but the MAVEN argon figures provide a good minimum estimate for the total amount of CO2 that's been lost into space. As for the reasons why so much of the Martian atmosphere has been lost into space compared to, say, Earth or Venus, well, that's simple. Mars is a much smaller planet, only a third the size of the Earth and Venus. Therefore, its core cooled and solidified much more quickly. And without a liquid core, the Martian geodynamo, which generates the magnetic field, in other words, the Martian magnetosphere, needed to protect the planet from sputtering and solar winds, would have quickly died out. This is Space Time. I'm Stuart Gary. Earth's rotation is slowing down, but a new study claims it's not slowing down quite as quickly as it should be. The findings, reported in the Proceedings of the Royal Society, are based on a study of hundreds of ancient eclipse records and lunar occultations. As the Earth's rotation slows down, the days gradually get longer, by about 1.78 milliseconds every century. This slowdown is caused by the gravitational tidal interaction between the Earth and its moon. As the ocean tides generated by the moon slams into the continents, the Earth loses some of its rotational momentum. These gravitational perturbations are also causing the moon to slowly move away from the Earth by about 3 centimetres a year, roughly the same rate at which hair grows. Scientists, including the study's lead author Leslie Morrison from the Royal Observatory Greenwich, examined historical eclipse records from around the world, the oldest dating back to ancient Babylon in 720 BCE. However, if Earth's rotation rate was slowing down at the expected rate of 2.3 milliseconds every century, as calculated by previous models, that Babylonian eclipse should have actually occurred somewhere over the western Atlantic Ocean, rather than the Middle East. The discrepancy means Earth's rotation has gradually slowed down, but not as much as it should. Morrison says there have been about 1 million days since that Babylonian solar eclipse, and even a gradual slowdown in rotation retardation becomes evident. The authors calculate that Earth's spin should have slowed down by about 6 hours over the past 2,757 years. As well as the Babylonian eclipse, Morrison and colleagues also analysed the timing and location of eclipses from ancient Greece, China and other areas worldwide, as well as lunar occultations stretching back some 400 years. Other factors influencing the Earth's spin rate include the slow rebound of crust that was weighted down by massive ice sheets during the last ice age that have since melted away. And that's a problem which is now being accelerated by additional increased ice melting caused by man-made global warming, which is both real and getting worse, despite the untrue claims of the fossil fuel industry's climate change deniers. Global warming removes water locked up as ice, not just at higher latitudes but also higher altitudes everywhere. As the Earth rotates, all this additional water tends to pool around the equator, increasing the planet's diameter and slowing down rotation. It's the same angular momentum issue which an ice skater faces when she brings her arms inwards to spin faster and pushes her arms outwards again to slow down. It's that overall shift of the location of mass which is changing Earth's rotation. Superimposed on top of all of this are small decade-to-decade variations in spin rate. These glitches are detected in astronomical observations of occultations of stars by the moon. Occultations are miniature eclipses that occur when the moon passes in front of a distant star as seen from Earth. Variations are also caused by poorly understood momentum shifts between the Earth's liquid outer core and the solid mantle overlying it. Massive earthquakes also cause slight glitches in the spin rate. To find out more, Andrew Dunkley speaking with Dr. Fred Watson from the Australian Astronomical Observatory.
Yes, the Earth's rotation has slowed down. We know that. We can see its effect now that we're blessed with atomic clocks that give us very accurate timekeeping. We have to periodically insert a leap second into our time in order to keep atomic clocks and the Earth's rotation in sync. So that tells us, we know from since the time that we found atomic clocks that the Earth's rotation is slowing. What's interesting, though, is that it's not slowing quite as fast as people thought it should. And what has happened, and the reason why we're talking about this, is that some scientists in the UK, in fact, 2 of them are people I know well. They're former colleagues of mine in the Nautical Almanac office, which was where I started my career in government astronomy.
Oh, wow.
These scientists have looked at records of eclipses and other astronomical phenomena dating back to 720 BC. And so what they've been able to do from this is plot out what the actual slowdown of the length of the rotation of the Earth is in terms of the increase in the length of the day. And they get a value for that of an average change of the day increasing by, wait for it, 1.8 milliseconds every century.
Right.
So that, you sound underwhelmed there.
Well, it seems insignificant, but you're going to tell me it's not.
Well, it's not, no, because if you don't do anything about it, that quickly builds up into a loss of synchronization between clocks and the rotation of the Earth. And before you know where you are, the seasons are all out of step with where we think they should be in the calendar, and get general chaos. So it is important. But what is, I guess, more important about this is the scientific information that this is giving us about things in connection with the Earth itself. So the evidence from these eclipses and what we call occultations, which are when the moon passes in front of or hides another celestial object, usually a star, but sometimes an asteroid or a planet. They're called occultations because the word occult means to hide, so that the moon does this. And they've been very accurately timed, really, since the invention of the telescope. So that goes back 400 years. And then you've got these eclipse observations that go back to 720 BC. And by combining them, these scientists have got this evidence that the rotation, the average slowdown is 1.8 milliseconds per century. But we have other information which comes from observations of the moon, observations of the distance of the moon, which you can make very accurately by bouncing lasers off the retroreflectors that were left on the moon's surface by Apollo astronauts. Combining that and combining evidence that comes from satellites in orbit around the Earth says that the slowdown should be 2.3 milliseconds per century. Which is half a millisecond per century more. So that figure of the 2.3 milliseconds per century is basically the effect that the moon is having on slowing down the Earth. The moon raises tides on the Earth. Those act as a braking mechanism on the Earth. And in fact, the energy of that is transferred to the moon. And so we know that the moon causes the Earth to slow down. But it seems that the moon causes the Earth to slow down by more than what we actually observe when you look at all these ancient observations. And so you've got this half a millisecond per century, effectively an acceleration in the Earth's motion. And that is the mystery. So this has uncovered something that we do not as yet understand. We've got a fairly good idea what it's caused by, but this half millisecond per century acceleration of the rotation of the Earth is unexpected. And that's why this is interesting.
Okay. Now, we're basing this on data that dates back to the Babylonians, right?
Indeed.
Okay. So I'm thinking they used a Windows abacus instead of an Apple Macintosh abacus, and therein lies the problem. But on a serious note, I mean, they didn't have the technology then, so could there be inaccuracies that we're not accounting for or don't even know about?
No, because when you amass all this stuff together, it's quite overwhelming, the amount of data. And all you need, actually, you don't need a time for this eclipse. You simply need to know that the place on the Earth's surface was eclipsed in order to be able to do this calculation.
Right.
In other words, because the moon's shadow across the Earth's surface is so narrow, if a place experiences an eclipse, and that's what all the record needs to say, then you can actually feed that into the calculation. And you get this really strong average value of 1.8 milliseconds per century. Basically, the bottom line seems to be that it is things to do with the Earth itself rather than the pull of the moon on the Earth that are causing this discrepancy. And what people are suggesting, two things. First of all, the fact that 11,000 years ago, the Earth was just coming out of an ice age and a lot of ice was melting. And that means that the mass of the material on the surface of the Earth was being redistributed. So the weight of the ice pushing down on the polar caps of the Earth, that's released when you've got this major melting 11,000 years ago. And what that does is causes a change in the shape of the Earth that's big enough to affect its rotation. That's one thing. And the other is the interaction between material down at the bottom of the Earth's mantle, which is a couple of thousand kilometers below our feet. That's more or less where the core of the Earth's iron core, starts. And there is thought to be an interaction between those two as well. So these two things together are probably what causes the discrepancy. So as I said, it's interesting that these ancient observations, this brings together archaeology as well as the most up-to-date science. But when you look at all those, what you're finding out about is the shape and mechanism of the Earth itself, rather than anything to do with timekeeping. And I think that's a really neat piece of science.
It is indeed. And I've thought of another factor, and this is my incredible anti-astronomy brain working here, but we have spoken in the past about the fact that the moon is moving away from the Earth gradually, and so one wonders if that reduces the influence the moon is having on the tidal effect and thus altering the calculations.
In fact, it's the tidal effect that causes the moon to move away from. So that is how you know that the moon's braking effect is 2.3 milliseconds per century.
So I've actually come up with the opposite answer to reality.
Yeah. No, it's all about cause and effect.
I told you it was anti-astronomy. It is amazing, though. Yeah, really interesting. I just love the way these problems surface, and then we've got to spend decades trying to figure it out. I think that's great.
In this case, that's right, because in some ways, one of the least well-known parts of the universe is the Earth under our feet, because we can find out a lot about the internal structure of the Earth from seismology and things of that sort. But when it comes to the details, and this is merging on the details here, or verging on the details, then it's really difficult to actually work out what's going on. And so this helps to shed some light on that.
That's Dr. Fred Watson from the Australian Astronomical Observatory speaking with Andrew Dunkley on our sister program, Space Nuts. And this is Space Time. I'm Stuart Gary. If you want more Space Time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. And time now to check out the night skies of April on Skywatch. Jonathan Alley can't join us this week, so I'm going to have to try and do this solo. Let's see how we go. High in the southern sky during April is the Southern Cross and its two pointer stars Alpha and Beta Centauri. The more distant of the two pointers is Alpha Centauri, the nearest star system to our own. Located some 4.3 light years away, Alpha Centauri actually consists of three stars: Alpha Centauri A and B, which orbit each other, and Proxima Centauri, which orbits the pair and at roughly 4.25 light years distant is currently the closest star to the Earth other than the Sun. Like the Sun, Alpha Centauri A is a spectral type G yellow dwarf star. It has about 1.1 times the Sun's mass and just over 1.5 times its luminosity. Alpha Centauri B is a spectral type K orange dwarf star, a little smaller and cooler than the Sun, with about 0.9 times the Sun's mass and about half its luminosity. Alpha Centauri A and B orbit each other around a common centre of gravity every 79.91 Earth years. The distance between them varies from about the distance between Pluto and the Sun to that between Saturn and the Sun. The third star in the system, Proxima Centauri, is a spectral type M red dwarf star, about 1/7 of the diameter and about 1/8 of the mass of our Sun. It takes about 550,000 years to orbit around Alpha Centauri A and B. The nearer of the two pointer stars to the Southern Cross is Beta Centauri. It's also a triple star system, but located a more distant 390 light years away. All three are young massive blue stars, far larger and more luminous than the Sun. Two of the stars, named Beta Centauri AA and AB, orbit each other, while the third star, Beta Centauri B, orbits the pair every 1500 Earth years. Beta Centauri AA and AB are known as spectroscopic binaries, meaning they're detected by spectroscopic data showing the two stars in the system are moving towards and away from us. The two stars orbit each other every 357 Earth days. Both stars are nearing the end of their lives on the main sequence. They'll soon run out of hydrogen for core nuclear fusion, begin the process of expanding, and eventually blow out to become red giants. Okay, from the pointer stars, we now move to the Southern Cross, or Crux, the smallest but one of the best known of the 88 constellations in the sky. During April, the Southern Cross lies on its side in the early evening skies, but it becomes much more upright as the night progresses. The bottom and brightest star in the Southern Cross is known as Alpha Crucis, or A Crux. It's actually a multiple star system located some 321 light-years away. Alpha Crucis consists of 3 stars: A1 Crucis, which is a spectroscopic binary, and A2 Crucis. A2 Crucis and the primary star in A1 Crucis are both spectral type B blue stars. They have surface temperatures of 26,000 and 28,000 Kelvin respectively. That compares to the Sun's surface temperature of around 6,000 Kelvin. The two components orbit each other every 1,500 Earth years at an average distance of about 430 astronomical units. The spectroscopic binary A1 Crucis is thought to comprise 2 stars with about 10 and 14 times the mass of our Sun, respectively. The pair orbit each other every 76 days at an average distance of about 150 million kilometres, or 1 astronomical unit, the average distance between the Earth and the Sun. A2 Crucis and the larger component of A1 Crucis are both expected to go supernova, ending up as neutron stars, while the smaller component of A1 Crucis could survive as a white dwarf. The left arm of the cross, the second brightest star in the Southern Cross in fact, is called Beta Crucis, and it's also a spectroscopic binary consisting of 2 stars. These stars orbit each other every 5 Earth years at an average distance which varies between 5.4 and 12 astronomical units. The primary star, Beta Crucis A, is a spectral type B Cepheid variable blue star, which changes in brightness over a period of about 4 to 4.6 hours. It has about 16 times the Sun's mass, about 8 times its diameter, and a surface temperature of around 27,000 Kelvin. The second star in the system, Beta Crucis B, is about 10 solar masses. A third companion has also been identified in the system. However, it appears to be a low-mass pre-main sequence star, which hasn't yet commenced nuclear fusion. Next, we come to Gamma Crucis, which is located at the top of the Southern Cross. It's the third brightest star in the constellation and also the nearest red giant to our own solar system, located just 88.6 light-years away. Visually, it's the nearest star to the 2 pointer stars. Although only 30 times more massive than the Sun, its expanded outer envelope has bloated out to some 84 times the Sun's diameter, and it's radiating some 1,500 times the luminosity of the Sun. As a red giant and no longer on the main sequence, Gamma Crucis is nearing the end of its life. Its surface temperature is 3,626 Kelvin, and it has a very prominent reddish-orange appearance. The star on the right-hand side of the Southern Cross is Delta Crucis, a massive, hot and rapidly rotating star that's in the process of evolving into a red giant and will eventually end up as a white dwarf. The star is located some 345 light-years away. It has about 9 times the Sun's mass and about 8 times its radius. It's presently radiating some 10,000 times the luminosity of our Sun from its outer atmosphere at an effective temperature of 22,570 Kelvin, causing it to glow with a bluish-white hue. The smallest star in the Southern Cross is Epsilon Crucis, which is located on the right-hand side in the space between Delta and Alpha Crucis. It's another red giant, some 228 light-years away. It has about 1.4 times the Sun's mass, and its bloated circumference is now some 32 times that of the Sun. Its surface temperature of 4,148 Kelvin means it's sometimes referred to as an orange giant. Let's now turn our eyes to the northwest and the constellation of Orion the Hunter. Orion's best recognized as a rectangle of 4 stars surrounding a central trio of stars which form Orion's belt. Hanging from the belt and pointing upwards from our point of view in the southern hemisphere is the Sword of Orion, also made up of what looks like 3 stars. However, the central star isn't a star at all. It's actually a massive stellar nursery known as the Great Nebula of Orion. It's located some 1,500 light-years away, making it the nearest large star-forming region to our solar system. Inside the Orion Nebula are hundreds of newly forming stars and protostars. The 4 best known of these young stars are called the Trapezium. To the right or east of Orion is the constellation Gemini and its 2 brightest stars, Pollux and Castor. At this time of the year, the Gemini twins are almost directly due north for Southern Hemisphere skywatchers. The higher of the two stars, Pollux, is a red giant 11 times the diameter of the Sun, just 34 light-years away. The other star, Castor, is much further away at some 51 light-years. It's not a single star, but a double binary made up of two sets of two stars, each double star pair orbiting the other every 460 Earth-years. A third reddish star, also a double star, has also been identified in Gemini. The stars are also spectroscopic binaries. Once again, that means they're detected by spectroscopic data, which shows the stars in each system moving towards and away from us. In Greek mythology, Pollux and Castor protected the sailors on the ship Argo, the ship searching for the Golden Fleece. Okay, let's turn our eyes eastwards now in the night skies, and we find the star Regulus, the brightest star in the constellation Leo the Lion. Regulus, which means Little King, is located 77 light-years away and has about 3.5 times the mass of the Sun and is about 140 times as luminous. Regulus is a binary companion star which takes some 130,000 Earth-years to orbit the primary star. Now, looking to the right of Regulus and virtually due east in the night sky is the star Spica. Located directly below the four stars in the constellation Corvus the Crow, Spica is another spectroscopic binary, comprising two extremely close stars orbiting each other every 4 days. In fact, the two stars are orbiting so close to each other, their shapes have been gravitationally distorted into the shape of a rugby league or gridiron football. Because of this distorted shape, light from the binary changes in brightness as the two stars orbit each other, exposing their elongated hemispheres towards us. Spica is located some 260 light-years away and is some 2,000 times as luminous as the Sun. Spica means ear of wheat, so named because it marks the start of the harvest season in the Northern Hemisphere. Going back to the Southern Cross now, and just to the right or west, we find the star Canopus, the second brightest star in the night sky after Sirius. Even though Canopus is 312 light-years away, it looks incredibly bright because it's so huge. In fact, it's a spectral type A blue star, 100 times the diameter of the Sun and 10,000 times as luminous. Its name's generally considered to originate from the Greek mythological Canopus, who was a navigator for the fleet of Menelaus, king of Sparta, who was sailing back from the Battle of Troy. Canopus is said to have died as the fleet arrived in the port of Alexandria in Egypt, and so the star, which was visible on the horizon at the time of his death, was named in his honour. Canopus is the brightest star in the constellation Carina the Keel. Carina is the keel of the ship Argo, again made famous in the search for the Golden Fleece. Carina, together with two other constellations, Vela the Sails and Pappus the Stern, were originally part of a super constellation called Argo Navis, or the ship Argo. Argo Navis was divided into 3 separate constellations in 1930, when the International Astronomical Union defined 88 official constellations. One of the nebulae in Argo Navis is the Great Nebula of Carina, a massive cloud of gas and dust between 6.5 and 10,000 light-years away. It surrounds the Eta Carina binary star system, located some 7,500 light-years away. The two stars of Eta Carina are classified as highly luminous spectral type O blue hypergiants. The primary star is estimated to be between 150 and 200 times the mass of our Sun. It has some 5 million times the Sun's luminosity and some 800 times its radius, with a surface temperature of up to 32,500 Kelvin. As we said earlier, the Sun's surface temperature is around 6,000 Kelvin. The companion star, although smaller than the primary, is still some 80 times more massive than the Sun and has at least 20 times the Sun's radius. And it's even hotter than the primary, with surface temperatures around 37,200 Kelvin. The two stars orbit each other every 5.54 Earth-years, cocooned in 2 gigantic lobes of gas and dust known as the Homunculus Nebula. Eta Carina has experienced a series of tremendous outbursts. During one event between 1830 and 1840, it suddenly became almost as bright as the star Sirius, the brightest star in the sky after the Sun. Both Eta Carina and its surrounding shroud of dust generate huge amounts of infrared radiation, making it the brightest infrared source in the sky. The tremendous outbursts generated by the stars are a sign that they're both reaching the end of their lives on the main sequence and are expected to go supernova in an astronomically short space of time. When it does go supernova, Eta Carina will be visible in daylight, and it may even become brighter than the full moon for months on end. April's night skies also sees Jupiter, the king of planets, in opposition. Opposition means Jupiter will be directly opposite the Sun as seen from Earth. Through binoculars, you should be able to see Jupiter's 4 Galilean moons, Io, Europa, Ganymede and Callisto. Through a decent telescope, Jupiter's cloud belts and zones are easily visible, and the Great Red Spot can be seen beginning its transit or crossing of the disk every 10 hours. And finally for now, this year's second major meteor shower, the Lyrids, will peak on April the 22nd and 23rd. The Lyrids appear to radiate out from the constellation Lyra, close to the star Vega, one of the brightest stars in the night sky this time of year. The actual source of the meteor shower are particles of dust and debris shed by the long-period comet C-1 Thatcher. Skywatchers in the northern hemisphere will get the best view of the Lyrids. However, those at mid-southern latitude should also be able to see the shower between midnight and dawn. Patient observers will be rewarded with around 18 meteors per hour before dawn from a dark sky location. And since the moon will be nearly at new moon phase, you can expect excellent moonless viewing conditions this year. Just look towards the east. The actual new moon will be on April 26. SpaceX has made history, becoming the first space operator other than NASA during the Space Shuttle program to successfully reuse an orbital-class launch vehicle on a second mission. A Falcon 9 rocket, previously used to deliver the CRS-8 Dragon cargo ship to the International Space Station in April 2016, has now been reused to successfully launch the SES-10 telecommunications satellite into orbit. The 70-metre tall Falcon 9 blasted off from Launch Complex 39A at the Kennedy Space Center at the Cape Canaveral Air Force Base in Florida.
T-minus 20.
Falcon 9 is configured for flight.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff of Falcon 9, the world's first reflight orbital-class rocket. Falcon 9 has cleared the tower.
With throttle back up, Falcon 9 continues to head downrange. Trajectory is nominal. We're past maximum dynamic pressure. That's the portion of the flight where the velocity of the vehicle combines with the density of the atmosphere at lower altitudes to put the greatest stresses on the Falcon 9. We're through that critical phase of flight. The next major event coming up in about 35 seconds, main engine cutoff. Coming up in about 20 seconds, we'll shut down the 9 Merlin engines, separate the first stage, and light the upper stage.
2 minutes and 40 seconds after launch, the first stage burn was complete. Its 9 Merlin 1D kerosene and liquid oxygen-fueled engines were shut down, and the stage was jettisoned, allowing the Falcon 9 upper stage to ignite its single Merlin 1D vacuum engine for the first of 2 burns to take the SES-10 satellite into geostationary transfer orbit 32 minutes after launch. The flight saw the first stage successfully return to Earth 8 minutes after launch, touching down on the pre-positioned floating platform, whimsically named Of Course I Still Love You, some 300 kilometres downrange in the North Atlantic Ocean. SpaceX boss Elon Musk named his 2 drone landing ships Of Course I Still Love You, which is positioned in the Atlantic, and Just Read the Instructions, which is positioned in the Pacific, after the planet-sized culture starships which first appeared in science fiction writer Ian Banks's novel The Player of Games. The Falcon booster is now expected to be refurbished for a third launch in what's being seen as the future direction of spaceflight. So far, 9 Falcon 9 first-stage boosters have now successfully been flown into space, then jettisoned to undertake a controlled return to Earth, landing for refurbishment and reuse on future missions. Reusing the boosters is expected to cut more than 10% off the $62 million price tag for a Falcon 9 launch. The ultimate aim of the program is to eventually be able to refly the boosters within 24 hours of a previous launch. This flight also saw the payload fairing, used to protect the satellite during atmospheric flight, return to Earth in a controlled landing for the first time. This was achieved by coating each half of the nose cone-shaped fairing with a special ablative paint designed to combat the heat of atmospheric re-entry. The fairings are also fitted with small reaction control thrusters and steerable parasols to guide the segments towards the recovery vessel. Once recovered, the fairings will also be refurbished for reuse. As for the SES-10 telecommunications satellite, it was successfully placed in its transfer orbit and is now moving into its final geostationary position. The Airbus-built satellite is based on the Eurostar E3000 platform and equipped with 55 Ku-band transponders, providing satellite TV and broadband coverage across Central and South America. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important, or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.